Weiler from Walther-Meissner-Institut, and he'll tell us about non-collinear spin dynamics and magnetic insulators.
Okay, so thank you very much for the introduction. Well, thank you, Joe, for inviting me. It's a great pleasure to be here, and so far I learned a lot in particular about spin superfluidity, and apparently I also learned that I really need a new computer. So now we're all set up. Okay, so before I begin, I have to acknowledge, of course, the people who contributed to the study. So it's done at the Walther-Meissner-Institut, and so this is kind of like a list of people who are involved in mechanization dynamics in particular. Stefan, Hannes, PhD students, master students, and well, down here, these are the postdocs and Rudolf Gross, head of the institute. With collaboration, TU Dresden, with Sebastian Gönnwein, who was previously at Walther-Meissner-Institut, with samples from University of Groningen, Aisha and Tom, and also theory support, Maxime Mostovoy, and also Andrei Leonov, Hiroshima University. Further samples, and I'm going to talk about these particular, are from Innovent. So let me begin with a short motivation of why we're actually interested in insulating spintronics. I guess you all know that, right? Well, Moore's law has been ruling the semiconductor industry for quite some time now, right? But already now, for the past, well, more than 10 years, right, our clock speeds have kind of like flattened out, right? We had these 3 gigahertz approximately, and it's just not moving upwards anymore, right, for quite some time now. That's mainly due to a heat limit, and more fundamentally, also, we know that structure size of our semiconductor chips is approaching quantum limits or eventually atomic dimensions, so we need to come up with some new ideas to get going with future information processing, right? And already this year now in 2017, there isn't kind of like a new downscaling of the Intel processors. So previously there was always the so-called tick-tock law, where every second year there would be a downscaling of the processes, and the other year there would be some refinement, and now there's kind of like 2 refinement years and 1 new technology years for the Intel processes. So that's why semiconductor industry thinks, okay, we need possible alternatives to the present technology, right? And well, one of these alternatives might be spintronics. So spintronic memory, you can already buy that. And well, for computation, it would be great to actually utilize spin orbitorks. I think that is a very promising approach, right? And well, it can be done with metallic ferromagnets. Of course, there's also a lot of studies in that direction, right? But in particular, in the context of this workshop here, of course, we're interested in, can we also use like insulators to do that? And in particular for this talk, can we actually use insulators that have some like more interesting magnetic structure than just ferromagnetic ordering? So, well, of course, the principle, yes, so both sides have already been shown. So we can use, well, complicated magnetic structures such as fermions, and well, spin orbitorks do work, so you can apply current pulse here. So this is work also done by Mathias and Geoffrey Beach groups. And then you can see, well, at least some of the fermions move with the current pulses, right? So spin orbitorks on non-trivial magnetic structures seem to be an effect, and also very recently it has been shown that if you use this thallium iron garnet, which is a magnetic insulator, put platinum on top of it, and then again apply current pulses to the platinum, so there's a perpendicular magnetic anisotropy material, you can actually switch it from up to down, right? So the spin orbitorks also work with insulators. And now, of course, interesting question is, can we actually combine these two, right? Look at insulator with complicated spin texture and use current or whatever to drive dynamics. So mechanization dynamics, so short overview at Walther-Meissner-Institut. Hans already told you about this part here, hybrid systems, right? Strong coupling, so that's one thing that we do. We study a lot of inverse spin orbitorks in various systems. We're also interested in dynamics, spin dynamics, systems with non-collinear magnetic ordering, with broad range of experimental tools, and of course also facilities for material fabrication. So for this talk, I'm going to concentrate on this topic here, non-collinear spin dynamics, and the technique will be broadband magnetic resonance. So this is the outline. of my talk. So first of all, I'm going to give a short introduction to broadband magnetic resonance spectroscopy. I'm going to talk about magnetostatic modes, so that's dipolar interaction. It's causing non-collinear dynamics in yttrium iron garnet, and then about this more complicated material, so the copper selenide, which is a skyrmion host material, and we're going to study the dynamics in this material. So let's start with this part here, the broadband magnetic resonance spectroscopy. I don't think I really have to explain that to you, right? You all know the Landau-Lifshitz Gilbert equation, all know and love it, and well, the solution to that obviously is the Polder susceptibility, where we can write the dynamic component of the magnetization as a function of the driving field, right? And well, the constant of proportionality, so to say, in linear response is the Polder susceptibility. And the nice thing about the broadband magnetic resonance technique is now that when we do these measurements, where we place a sample, some dimensions of length L and thickness delta on top of our coplanar waveguide, and we do the measurement, that we're actually able to use a vector network analyzer to measure a property which will turn out to be directly proportional to the susceptibility. So that's, of course, very powerful for quantitative analysis. And it comes about that the dynamic part of our magnetization MX here is generating a magnetic induction B which threads around the semiconductor, and that, by Faraday's law of induction, gives rise to an AC voltage along the y direction, right? And that voltage at the frequency of the magnetization precession, which is also the frequency of the driving field, is what we measure in the experiments using phase-sensitive detection. So once you do that, it's a matter of some small data processing here to get rid of the frequency-dependent background that you have in these measurements, right? Because the transmission is obviously not perfectly one. And if you do so, then the typical spectra will look like this, with the real and the imaginary part of the measurement. And if you compare that to the susceptibility, so this is the real part, the blue, and the yellow one is the imaginary one, then you see it's in perfect agreement, because you need to consider this factor minus I, which comes from Faraday's law of induction. So this is kind of like a quantitative agreement, and I want to point out that there's this inductance L, which is given by this expression. So this is kind of like really fully quantitative, and now also to the point that we don't really need a fit anymore. So this is still a fit, but I can actually plot the theory, and it quantitatively matches with the experimental data points rather well. Okay, so with this spectroscopy tool, what can we do? Well, for the purpose of this talk, what we're going to study using it is the resonance dispersion and the line width. And well, for a simple ferromagnetic or ferrimagnetically ordered material, let's say uniform mode precession, it's rather simple. We apply the external magnetic field for a thin film sample along the z direction here, and you measure the resonance field and the line width, which you extract from the fits to your data. They both scale linearly, as one would expect from Kittel equation and the Gilbert damping respectively. So it's kind of like a powerful tool that we use for sample characterization. So now let's get started with the actual interesting stuff. So first of all, I'm going to show you some results that we obtained using a very well-known magnetic material, yttrium iron garnet, right, and studying dynamics in that material. And well, a ton of it has been done in the 1960s, but what we're adding to the old studies is in particular that we now have this broadband magnetic resonance spectroscopy tool and not cavities which operate at a fixed frequency. So we are in a position where we can learn about damping and not only about line width. Okay, so magnetostatic modes, well, titled this theory, it's kind of like a hand-waving argument. It's based on dipolar interaction. You can visualize something like that if you have this board with the compass needles, right? And I think there's several messages you can take away from that. Is well, first of all, it's really long range, right? So it's turning out to be kind of like independent on the actual size of the sample. So it's long range. It's going to be dependent on the shape of the sample, whether it's rectangular, cubic, spherical. It's going to look distinctly different. But in any case, it's going to be very complicated, right? So nobody would be able kind of like just say, okay, well, this is how it has to look, right? The equilibrium orientation. So it's complicated. Meaning, if you want to know the theory, you have to read papers from the 1960s. Okay, so I'm just going to show the very basic idea for the theory. You start with the Landau-Lifshitz equation. Neglect the damping term. You linearize the Landau-Lifshitz equation. Now we're going to look at a spherical sample, right? So that's where you have the demagnetization term NZ in here, which is 1/3. And we end up with this linear equation, and you solve it using these conditions here. You can read it up in this paper how it is done. So this is the solution, and well, the solution, the P is just Legendre polynomials. This theta here is a quantity which is related to the magnetic susceptibility, some intricate, complicated fashion, and N and M are mode indices, and nu finally is the resonance frequency. Okay, so this is how it looks from theory. So what is it microscopically? So this is uniform mode precession. Magnetization has this dynamic component mx, and now just plotting the dynamic component mx on a sphere, right? The uniform mode would look like that. So it would be the same at any point within the sphere. So that uniform mode in this formalism here, it has the indices 1, 1, 0. Okay, so 1n, 1m, and the last one is just the number of solutions. So kind of like first solution you get for this equation. So that's kind of like the boring mode, uniform mode, Kittel mode, ferromagnetic resonance, however you like to call it. And then you can play around with these numbers arbitrarily, and for instance plug in 2, 1, and you get this solution over here, where the dynamic component is actually out of phase on the top and bottom side of the sphere, for instance, right? And well, there's an infinite number of solutions, obviously, as you can see from this here. Okay, so for these two modes, for instance, you can plot the dispersion, right? So frequency, magnetic field. What's interesting is to note here is that actually at a fixed external magnetic field, the mode with the lowest frequency is not necessarily the uniform mode, right? So here the 210 mode has actually a lower energy, a lower frequency. So it's maybe a bit counterintuitive. Okay, so it's all summarized in this publication here. So our question is now, well, this magnetostatic modes and spheres, so this has been very well known, right? So, but what about the damping of these different magnetostatic modes? So what can we learn from the damping, and is it actually necessary to consider the magnetostatic interaction of these different modes if one really wants to extract the damping of the X sphere, right? So doing that, the experimental setup that we use is rather straightforward. So we use a coplanar waveguide where we put the yttrium iron garnet sphere, right? So we learned it's green. So we put it on top of our semiconductor, and actually the semiconductor and the yttrium iron garnet sphere, they were like both 300 micrometer, meaning that we get a non-uniform driving field at the position of the sphere, which is evidently needed to drive any non-uniform mode, right? And then, well, you can do spectroscopy, fixed magnetic field as a function of frequency for different modes. So this is just an example how it looks like. I can fit the data. Okay, so doing that, so this is kind of like what I showed before, like, so this is what we would expect, and well, this is the corresponding experiment, and now just to confuse everybody a bit, there's a renormalized frequency axis, so we subtract the resonance frequency of dpph, oh, sorry, I forgot to say that, it's the black point down here, some dpph, right, some paramagnetic system, which we just use as a marker because it's very well known from literature what the chi factor of this material is. So this is a reference to calibrate our external magnetic field. Okay, so we normalize everything we measure to the dpph, meaning if you see a perfectly vertical line in here, then the chi vector of that mode is identical to that of dppH, right? So, and if it's kind of slanted a bit, then the chi factor is slightly different. Okay, so that's what we are, where we are at. And now it's very simple to identify these modes, right? You just have to calculate all of them, which is an infinite number, and then figure out which one is which. Okay, so this is just an exercise in patience, right? So you kind of like go and plug in all different numbers, and then when you identify one which actually matches to the measurement, so measurement here shown, extracted from these data as the symbols, and the lines are the calculated modes, right? And then you find agreement, and you're happy, and you move on trying the next 500 modes until you find one which matches again. So this is kind of like the very intelligent algorithm to determine the mode numbering, right? But nevertheless, in apparent infinite time, it's possible to do so. And the first thing you notice is, well, some modes appear to have a very strong intensity, and it's not the uniform mode, right? It's some modes over here, and the explanation for that is that these modes here, which are particularly strong, they have a strong localization of the mode or strong dynamics close to the center conductor, right? So the driving field is much weaker if you go further away from the center conductor, and that's why these modes are particularly strong. Okay, so more interestingly, so this is the resonance field, so nothing new over here. We can now look at the line width of the mode as a function of resonance frequency, and that's where things are starting to get more interesting, because you can now see that the slope which corresponds to the Gilbert damping of all these modes is identical, right? So meaning the Gilbert damping is really independent of mode number, and this data here tells you that the Gilbert damping for our sphere, this is 3 times 10 to the minus 5, which is actually lowest number ever seen on any magnetically ordered material, which is very nice, right? And then you have the offset here, so the inhomogeneous broadening, and that is already well discussed in the old papers I showed before. That is actually due to surface pit scattering. It's coming from the fact that the sphere is not a perfect sphere, but because of this rather crude polishing steps that are done to fabricate it, it has dimples on the surface, right? And that causes an inhomogeneous broadening of the lines, but we do actually understand it rather well also. Okay, so that's kind of nice. So we can see a very low damping, and now let's look at the temperature dependence, right? So those already mentioned in talks before, that kind of like cooling down yttrium iron garnet is not really helpful, because one knows that the line width actually increases. So let's see what we can add to that story. So this is a measurement, well, basically exactly the same setup, right? We have the dppH marker, the yttrium iron garnet sphere, but now everything's mounted obviously in the VTI of a magnet cryostat. Can record it at room temperature again, 290 Kelvin, and we'll get this mode spectrum. And if you compare that to the mode spectrum I showed previously, we can again identify the modes, and it's kind of like very difficult to see, but there's a red dashed line on that mode and a red dashed line on that mode, and those are identified as the 110 and the 440 modes. And for the temperature dependence, because we already learned from the room temperature data that the damping is the same for all of the modes, we're just going to focus on these two modes. Okay, so can go to lower temperatures. So this is 20 Kelvin. Well, there's the 110 mode over here, the 440 mode over here, right? And what can we learn from it? So I cut this little red line here, shows the cut that we're doing here. Looks like that. So data looks pretty ugly over here, but actually the raw data is rather okay. You can definitely fit it. So there's a fitted line in there. You can extract the line width and the resonance frequency. So first of all, looking at the resonance frequency, the resonance frequency for the 110 and the 440 mode are given by these two expressions, right? And you can see if you compare just the difference of resonance frequency, you're able to extract the saturation magnetization. It's actually a very nice way to do so, because it will only depend on the absolute frequency that you actually measure, and that is going to be very exact with the VNA, right? So that's going to be good within 10 to the minus 9, right, the frequency. Meaning there is, it doesn't matter how exact your field is, right, because you're doing this analysis in the frequency domain, and the H0 just drops out if you look at the difference. Okay, so you can extract the saturation magnetization as a function of temperature, right? So this line is a fit to Bloch's law, so that it's kind of like as expected, that works. You can look at some anisotropy field in the yttrium iron garnet sphere. So for the dppH, there is 0 anisotropy field. For the yttrium iron garnet, okay, there seems to be some variation with temperature. And you can look at the Chi factor, how that varies with temperature. Right, so it's shown here for the YIG and for the dppH reference, where the temperature variation is actually rather small in both cases. Right, so it's below 0.5% also for YIG. Okay, so now let's look at the line widths. So here again the example spectrum. So now we're looking at the delta F, and you can now look at the delta F at some fixed frequency, so 9.6 gigahertz or 28 gigahertz in these two cases here, as a function of temperature, right? And then you actually see, oh yeah, actually cooling down the system doesn't, or the YIG doesn't really help a lot, because it increases, and that is this very well-known result where the peak here is attributed to slowly relaxing rare earth impurities, and just phenomenologically, as an experimentalist, you can identify that it's slowly relaxing and not fast relaxing, because the peak actually changes when you change the frequency. Right? So that's kind of like the telltale sign, which we also observe in our experiment. So that was at, well, fixed frequency. So now actually look at the line width versus frequency as a function of temperature, right? So extract the damping. Well, there it turns out that at high temperatures, so 290 Kelvin here, room temperature, that obviously works. We did it before. At very low temperatures, we apparently don't have enough frequency, right? So eventually it should evidently increase, but judging from the plot, we would need to measure at least to 100 gigahertz to be able to do so, which is not possible, at least not at the moment. But nevertheless, for the frequency range where we can get a solid linear fit, which is down to about 100 Kelvin, we do see that the damping really decreases. And it decreases, well, the within errors completely linearly, and well, that dashed line extrapolated down to the lowest temperatures suggests that the damping really goes away completely if you go to 0 Kelvin, whatever that means. Then you can also look at the inhomogeneous broadening, just this intercept here. You can see it might slightly increase, but that's getting very difficult to disentangle from the onset of the peak, right, from any slowly relaxing impurities. So it might also be almost temperature independent. Okay, so meaning once you single out this relaxation with the rare earth impurities, then actually the damping decreases. And that means if you want to do now some things like cavity spintronics, strong coupling, if you do it at high frequencies, so high enough frequencies, then cooling down actually helps you, right? So it doesn't help you if a cavity at 5 gigahertz or something, because your line width is going to increase due to the slowly relaxing impurities. But if you're out here at 50 gigahertz or somewhere, then cooling down should actually improve things.
20K
yeah.
seems to have a negative slope.
Yeah. This is just right. It's kind of like, look at these data, right? The old data. It looks like there's a negative slope here, right? So if you, sorry, oh no, that's the wrong. Oh yeah, it's that one. Yeah, with negative slope. So what I'm saying is, what you're seeing in here is a peak towards low temperatures, right? Which is a slowly relaxing impurity. And if you go out to high enough frequencies, then eventually the alpha wins, right? And it will be a positive slope. Problem is we cannot go so high. You can see from this plot that at 20 Kelvin, right, the slope is essentially 0, right? There is, the Gilbert damping is completely switched off by going to so low temperatures, right? So that's kind of the point, that if you go to 20 Kelvin and you go to 50 gigahertz, right, so then apparently you win a lot compared to the room temperature data, But that's not the case if you go to 5 gigahertz, right? It actually gets worse if you cool it down. So it really depends on what frequency you design your microwave setup. So if you do high frequencies, cooling down actually helps. Okay, so that was the non-collinear dynamics, dipolar interactions. So now let's change the length scale of our interactions and look at this copper selenide material. So another quick primer, because it hasn't been explicitly mentioned so far. You're all familiar with the Heisenberg exchange causing either parallel or anti-parallel alignment of neighboring spins in a one-dimensional spin chain here. The DMI, again, just phenomenological impression, right? The DMI will cause a orthogonal alignment of neighboring spins, and the helicity or chirality, if you read it from left to right, is going to be either counterclockwise rotation going from left to right or clockwise rotation going from left to right, depending on the sign of the DMI, right? So, and it's a consequence of broken inversion symmetry and spin-orbit interaction. So we're looking for a material which has both Heisenberg and DMI, and an example for that is the copper selenide material, which is also a magnetic insulator. Right? It's fitting for this workshop, right? So that's a simple view. So we have to combine both interactions, and then the spin alignment should look something like that. So it's different from the case of the YIG with the magnetostatic modes, because the magnetostatic modes mean that they influence the dynamics, right? So in the dynamics, the phase of the precession is going to be different throughout the sample, but the equilibrium orientation is going to be still ferromagnetically aligned. Now the equilibrium spin orientation is already non-collinear, right? And also the length scale is drastically different. So the length scale here is set by the ratio of DMI and exchange, and it's somewhere in the order of a couple tens of nanometers. Okay. So some background info for copper selenide, right? So it has a very rich magnetic phase diagram. So it orders ferromagnetic or field polarized at elevated temperatures. And once you go below the Curie temperature, which is about 58 to 59 Kelvin, you get magnetic ordering, and depending on the external magnetic field, the magnetic ordering can be conical, skyrmion, or helical. And I tried to sketch these different phases here. So in the ferromagnetic phase, it's boring, right? So they're all in parallel. So ignoring that it's ferromagnetic and not ferromagnetic, they're all going to be aligned with the external magnetic field. In the conical ordering and in the helical ordering, the spins are going to be aligned, dominantly perpendicular to the external magnetic field. And you can see what's really interesting when you go from the ferromagnetic to the conical order is that now in the conical order there's a periodicity to the spin lattice, right? So you go from here to here, and that length scale is just about 10 to 100 nanometers, and then it's periodic again, and so on, right? Whereas in the ferromagnetic there is no characteristic length scale, right, in this picture. Okay, so helical and conical actually have very similar structure. The only difference being that in the helical, the projection of all the magnetic moments onto H0 actually vanishes, meaning the so-called pitch vector, the gray arrow, is not necessarily aligned along H0, but aligned along some crystalline axis, so it's set by anisotropy, whereas in the conical phase, it's actually aligned along the external magnetic field. Okay, so skyrmion phase, you already saw these pictures, right? This is complicated wall-like structure, which you can actually think of as just a superposition of three of these pitch vectors, right? So kind of like you take three of them with 120 degree to each other, and that gives you this picture.
This diagram is theoretical or experimentally?
Well, by now I would say both. So there exists theory which kind of like does real space or reciprocal space imaging of that, but this here is, well, I wouldn't even call it theory. It's kind of like I just draw it. it's not calculated. Oh, this one. Yeah. Oh, the phase diagram is experiment. That's what we determined for that sample. Yeah. So this phase diagram. So these points in here, like always with the phase diagram, right? A huge part of it is fantasy, but the data points are real, right? Okay. So and it's determined on the actual sample that we're using. Okay. So now dynamics, right? So ferromagnetic trivial, right? So it's all precessing in phase. Conical, each spin precesses about its equilibrium position. So it looks like that. And I can now look at the phase relation from one spin to the next. So the phase is encoded in color here in this little animation. And if you look closely, then you see that the color down here is always the same color as that up here. Okay? So meaning the one at the bottom and the one at the top, they precess in phase, and the one in the middle that precesses perfectly out of phase to that one here.
What do you mean by phase here? I'm confused. How do you define your phase in this case?
Well, let's say, so I would say I would define the phase if you flip all the directions of the spin so that the equilibrium orientation is in parallel, okay? Then you have like a classical phase like a spin wave, okay? So just take all the equilibrium orientations and rotate them like that, and then I guess that's what you would typically call a spin wave, right? Which has a certain phase relation, which continuously varies. Right, so basically, it's like a classical spin wave, which just told the equilibrium orientations. Okay, so that's how it looks in the conical, and it's equivalent in the helical, right? So just start doing it, but it's kind of like this is the fundamental mode that you get in the conical and the helical, and you can immediately see it's drastically different to the ferromagnetic, right? It's not all spins are precessing in phase, but there's some intricate phase relation, and the wavelength of this heliomagnon is set by the pitch length, right? So the periodicity of your dynamic excitation is the same as that of the equilibrium orientation, right? So it's this 60 nanometers in that case for our material. Okay. So now we can look at mechanization dynamics, right? So same old story. We put it on top of our coplanar waveguide, put it in the magnet cryostat, and then set our temperature and our magnetic field to be somewhere, for instance, here in the Skyrmion pocket. Right, so this little star here is actually the value of the magnetic field at the temperature which you use, and then we can record a spectra where we vary the frequency of our microwave and then see clear resonances, and those can be identified to the modes of the Skyrmion lattice. In this instance, we have anticlockwise and breathing mode dynamics. Okay, so this is covered in detail in this paper here. So this is not going to be the focus of the remainder of this talk. Okay, so we then obviously also can go to lower temperatures. So this is now same phase diagram expanded to lower temperatures, right? And this is where we are actually measuring now. We're going to set our temperature to 5 Kelvin and the external magnetic field, which in that plot is applied along the z direction, so out of plane or along the 111 crystalline direction of the copper selenide, and then we again do this frequency scan. Right, and this is the spectrum. So you can see there's a ton of resonances, right? And these resonances, they are actually magnetostatic modes, but they're magnetostatic modes not of a sphere, but of a cuboid sample, meaning that the demagnetization field is actually non-uniform, and not uniform in the sample, meaning it's not possible to calculate them analytically anymore, but you need some numerical code to get spectra like this. And our theory guys, Maxime and Andre, are trying to reproduce this. It looks very similar what they get, but getting quantitative agreement is impossible, I would say. You can just see there's a lot of resonances, okay, and it's compatible with magnetostatic modes. And it's not noise. They're all resonances, okay. And we're going to take a very bold assumption, and that is from all of these hundreds and thousands of resonances, if you zoom in, there's more and more and more, right? Because the number of modes is infinite. Right, the magnetostatic modes. So there's an infinite number of resonances in there. And we're just being very bold and say the lowest frequency one, we identify that as a uniform mode, which is not necessarily true. Okay, so but it will show later that it doesn't matter for the data evaluation which one you use. So there's maybe a 2 gigahertz error on the resonance frequency. Okay, but it fortunately doesn't impact the results. Okay, so there was data at 100 millitesla, and now we do a full field sweep. Right, so then the data looks like that. We're starting in the ferromagnetic phase over here. Right, you can see the frequency versus external magnetic field dispersion is linear and positive. Right, that's what you expect from a ferromagnet. You see the same magnetostatic modes, obviously. In the ferromagnetic phase, go to the conical phase, and dispersion becomes negative. Right, and they go to the helical, and well, again you see some discontinuity in the dispersion. And that's also how we construct the phase diagram. Right, it's kind of like easy to identify characteristic magnetic fields.
Can you tell anything about the order of the phase transitions if you do some frequency-based discussion?
What do you mean with
First order or second order phase?
Yeah, you should in principle be able to do so because what we also measure is basically the static susceptibility, and from that we can see whether it's continuous or not continuous, and it's continuous going from ferromagnetic to conical and conical to helical, and not continuous going to the skermion phase, right? So you can assign first and second order phase transitions using that. But it's not, I would say it's not perfectly clear at all temperatures, right? But at low temperatures it works very well. Okay, so this has already been more or less published in this paper, minus the magnetostatic modes. And the big surprise now is going to higher frequencies. Okay, so if we just measure to higher frequencies, so this is basically a continuous frequency scan at the same temperature as a function of magnetic field, then one sees, well, there appear additional modes, right, which are at higher frequencies than those modes down here. And well, one thing you notice, the magnetostatic modes don't seem to be such a big issue anymore at these higher modes, right? The number of resonances drastically decreases if you go up here. And well, also 20 gigahertz, if we had a VNA that went to much higher frequencies, I would guess you would see at least the next order also. So very importantly, in the ferromagnetic phase, there's nothing, right, at higher orders. Okay, so ferromagnetic phase, you see magnetostatic modes, and that's it. Okay, so this is also what you would expect. Okay, so question is, what are we actually seeing here? And well, first of all, that was for one orientation of the external magnetic field along the z direction. So we change it also along x and y direction. So that's c direction, x and y. So this is kind of like complete data set, all taken at temperature of 5 Kelvin. And it might look intimidating or complicated, but qualitatively, it doesn't matter what direction we apply the external magnetic field. So that's the message of this, right? So we always see 3 modes in the conical and in the helical phases, and no additional modes in the ferromagnetic phases, right? So there's nothing in the ferromagnetic, but there is something in the helical and conical modes. Okay, so we assign these sets of resonances numbers 1, 2, 3. And now let's think about what we're actually seeing. So
can I ask a question?
Yes.
Yeah. So this helical phase, this helical, this pitch, using the Finland, right?
So the pitch should be in a multi-Q domain state, right? So it should point along. I think it's the crystalline 100 or 111. I forgot. It's kind of like along a certain crystalline direction, right? The easy axis of the copper selenide, whatever that is.
In the plane or out of?
It's both in plane and out of plane, right? It's a cubic system, right? So it's kind of like if it's along the 100, it's along some weird directions, right? In that coordinate system or with that cut of the crystal. Right, so it's but it's definitely a multi-Q state, right? You can also see that in the helical, right? There's these 2 sets of resonances which are very clearly separated, which we think is the multi-Q, because you're basically seeing one which is dominantly like out of plane, giving you I think the low resonance frequency, and then the in-plane ones are rather degenerate because it's almost like a thin film, right? So you see these 2 different resonances.
You have domains of
Yeah, domain. It's called the multi-Q multi-Q state, right? Where you have in the helical phase, the external magnetic field is just not large enough to saturate it to the conical phase to pull the pitch vector along the field, right? So what's actually going on? So this is again the equilibrium orientation of spins, right? The helix length 60 nanometers for copper selenide, taken from literature value, and this is the fundamental mode dynamics. Okay, so that I already showed that. There's a side note, and that is if you integrate the dynamics from down here to up here, that mode is perfectly linearly polarized. Okay, so you're only going to see integral dynamics which are moving in a linear fashion. So that could be interesting for squeezing, if that's how squeezing works, right? You could say it's perfectly squeezed. Okay, so you can then think about the second order mode, and that's well a bit like a standing spin wave, right? You have a periodicity which is set by this length scale, or it can be half of it, right? It can be like that. So that's now the case that this spins here precess in phase with that halfway through the helix length. Okay, right? So color here and here is now identical, and then you can go on like same scheme, right? That's 1/3 and 1/4 and 1/5 and so on, right? And you can assign the different possible excitation modes of this spin spiral. Okay, so why is that actually interesting? So field of magnetic crystals. Well, there the goal is to do band gap engineering or do band structure engineering of the dispersion of a typically ferromagnetic material, and you do so in a top-down approach, usually by nanolithography, like shown here. Right, so you introduce some periodic modulation, which typically changes the demagnetization field, and that then gives rise to the band gaps in the structure. And well, everybody or people in the field of magnetics are excited because you can basically look at magnon propagation in this magnetic crystal, right, and maybe use it also for real data processing applications. Now, the interesting thing about the case of the copper selenide is, or of any spiral magnetic material, is that it has an intrinsic length scale, right, set, or an intrinsic periodicity set by this helix length, the 60 nanometer. So it's basically like a magnetic crystal with a lattice constant of 60 nanometer, which is challenging, not impossible, but challenging to fabricate with nanolithography. But the quality of that crystal, right, so this works over millimeter scales of the samples, right? It was 8 millimeters long. They have almost a perfect periodicity. I'd say that's impossible to do with nanolithography, right? Getting that resolution on 8 millimeter length scale, and this is the calculated dispersion of the of the dynamic excitation of that lattice here. And because I did this calculation, I cannot get this opening of the band gaps with the integer numbers because I did this yesterday evening, and I just couldn't figure out how to actually get it. But I'm sure if somebody from theory actually looks at that, it's possible to get the opening of the band gaps, right? And the opening of the band gaps just means there the dispersion actually has a zero slope, so that's where we can get the resonant excitations, right, at the integer numbers of this wave vector. Okay, oh yeah, and the equation to calculate the red line is taken from that paper here. Okay, and it's also printed here, so that's the equation. Okay, so that's what we do. So we assign 3 different modes to these 3 different dynamics, right, using this dispersion here. We label those 1, 2, 3, extract the resonance frequencies of the 3 modes, and we then can plot for all the different external magnetic field orientations. We plot these modes. So the data points are the extracted resonance frequencies, and the lines are fits, or is a global fit to all 3 modes and all 3 field orientations, and these are the resulting parameters that you get out of the fit. And the message here is just that for these parameters, they agree with what you would expect to get for the copper selenide, right? So it doesn't seem too bad. And also said, right, there is a certain uncertainty here with that mode right? Because of the magnetostatic mode. So the error bar here is actually rather large, right? It could be like 2 gigahertz error bar, but it's not too bad on that scale here, right? It doesn't make that much of a difference. So the fit results barely change. Okay, so well, that's almost all of the story. Final thing is, looking at the raw data, you already see that the lines are really narrow, right? So well, what's actually the damping of the system? And while extracting the damping, right, you need to do measurements at several different frequencies and then get the linear slope of it. Because, let me go back again, because of these different modes, we only have discrete frequencies where we can do that, right? So we cannot do it as a function of external magnetic field, as we usually like to do, because obviously in the system, if we change the external magnetic field, we are changing all sorts of properties of the ordering, right? So we have to do it at fixed field, and that leaves us, well, in the frequency range of our VNA with 3 principal frequencies, and then the lower one is governed by these millions of magnetostatic modes, so that drops out as well, leaving us with 2, which is perfect to do a linear fit, right? Okay, so these are the 2 different modes. Setting the external magnetic field to 30 millitesla, for instance, it doesn't really matter. Checked a couple different values, right? So you can fit these modes rather nicely. The n equal 2 and the n equal 3 mode. You can look at the frequencies. So for this case, and that's why I show this, the frequency is approximately double for the n equals 3 mode than it is for the n equal 2 mode on the line, which is approximately half. Right? So that's kind of like, well, perfect linear fit, right? Okay, well, this is just the equation. Okay, that's not so important. We just fit the field derivative of the susceptibility to the data because that's our data processing. But at the end of it, the alpha that we get, so estimating it as delta f over 2f, is definitely smaller than 0.003. And here we can only give an upper limit for the damping because actually our field resolution was not large enough to, or was not fine enough to really resolve it. So these lines are a bit over-modulated, which is considered in the fit, right? But this is an over-modulated line, resonance line. So this is only an upper boundary. And very recently, Dirk Rundler group, Stasinopoulos' first author, they looked at the ferrimagnetically ordered phase at low temperatures and found a damping of 0.001, which is definitely compatible with this value here, right? So meaning this is rather nice, rather low damping, right? So for a metallic system, this is already record value. It's not as good as YIG. There's still 2 orders of magnitudes missing. But it's a, well, skyrmion or conical system at low temperatures. It has very nice low damping. Okay, so let me summarize. So we're looking at non-collinear magnetization dynamics using broadband spectroscopy. And there's 2 very different regimes. So one is kind of like, well, the big size limit, dipolar interactions. We can look at magnetostatic modes and extract the damping. We actually find, well, damping of YIG is even lower than previously estimated. And it even decreases if one goes to low temperatures. And for the helimagnons, we also find very low damping, low temperatures. They're governed by exchange and DMI, and they form perfect natural magnetic crystals. Okay, so thank you.